Okay, now this is the introduction to statistics, and what we're going to do is we're going to go through some definitions that we're going to need going forward into the book. So let's get started. Okay, the first definition is the definition of data. And data are collections of observations. These could be measurements, gender, or survey responses, but basically they're just collections of observations. All right, now a statistic is the science, or sorry, not a statistic, but statistics as a field. Statistics is the science of planning studies and experiments, obtaining data, and then organizing, summarizing, and presenting, and analyzing and interpreting the data, and also drawing conclusions based on that data. So statistics is basically everything about data. Now, those collections of observations fall into two categories. Uh, A population is the complete collection of all individuals. So the population would be the complete collection of every score or person or measurement that you are going to study. Now, the collection is complete in the sense that it includes all of the individuals that are going to be studied. So, if you collect data from that entire population, then what you've done is you've collected a census. A census is a collection of data from every member of a population, while a sample is a sub-collection of members selected from a population. So there's a difference between a sample and a census. A population is all of the individuals to be studied, while a sample is a sub-collection of the population. So it's a sub-collection of all the individuals that are going to be studied. Okay, now a parameter is a numerical measure that describes some characteristic of the population. So for instance, if you add up all the values of the population, add up all the measures that you take and divide by the total size of the population, you get the population mean, which we're going to denote mu. Now, if you want to know how your population is dispersed, you can calculate another number called the standard deviation, which is denoted sigma. That would be the population standard deviation. And if you want to know what percentage of your population has a certain characteristic, you could divide the total number that have that characteristic by the total number in the population, and you would be getting the population proportion P. So those are some population parameters that we're going to look at. And there's a counterpart to the parameter is a statistic. And a statistic is a numerical measure describing some characteristic of a sample. So what a parameter is for population, a statistic is for a sample. So for instance, if you don't have the entire, if you don't have all the numbers from the population, but only the numbers from a sample, and you calculate the mean, you don't call it mu, which is the population mean, you call it x bar, which is the sample mean. And if you're going to calculate the standard deviation for the sample as opposed to the population, you don't call it sigma, you call it S. And for the proportion, it's not P when it's only a sample, it's called P hat. So these are some population parameters: the population mean, the population standard deviation, and the population proportion. And these are some sample statistics: the sample mean, the sample standard deviation, and the sample proportion. So let's take a look at these examples here to see if we can distinguish between populations and population parameters and sample statistics. So it says in exercises 5 through 12, determine whether the given value is a statistic or a parameter. Well, it would be a statistic if it comes from only a sample. It would be a parameter if it comes from the entire population. So this number 6 says amongst the senators in the current Congress. So the thing that we're studying is the senators from the current Congress. And 44% of them are Democrats. So that's 44% of the entire, of all the 100 senators in Congress. So that is the population size of senators. There are 100 senators in Congress. Of those 100 senators, 44% of them are Democrats. So now, since we're looking at the entire population of senators, all 100, this 44% represents P, the proportion of Democrats is 44%. And because we're talking about the entire population of senators, all 100 senators, this is actually a parameter and not a statistic because we're talking about the entire population. So this, for number 6, this value is a parameter. Now for number 12, the author randomly selects 35 movies and found that the amount of money that they grossed from ticket sales, the average or mean is 1,000 or sorry, $123.7 million. So the population here would be all movies. Our author randomly selected 35 movies out of the total lot of movies, and that constitutes a sample of all movies. So we're not talking about the entire population of all movies. We're talking about a sample of 35 movies. And we found the mean um, gross from ticket sales. And we found that to be 123.7 million. So, since this is only for my sample of 35 movies and not for all movies, this is not a parameter because it doesn't come from the population of all movies. This is a statistic because it only comes from my sample of 35 movies. So this is a statistic as opposed to a parameter. So in one case we have a parameter because this value is representative of all senators, and in one case we have a statistic because this mean is only representative of those 35 movies from my sample. All right, now let's take a look at these two definitions. Definition of quantitative versus categorical data. Now, quantitative data or numerical data consists of numbers representing counts or measurements, as opposed to qualitative or categorical data consist of names or labels and are not numbers that represent counts or measures. We also want to draw a distinction as far as quantitative data goes. There are two types of quantitative data. One type of quantitative data is discrete data, and it results when the number of possible values is either a finite number or a countable number. So that is what discrete data is. And continuous data results from infinitely many possible values that correspond to some continuous scale that covers a range of values with no gaps or interruptions or jumps. See, these gaps, interruptions, and jumps are really the distinction between continuous and discrete data. So let's take a look at these examples here. In exercises 13 through 20, determine whether the given values are from a discrete or continuous data set. Number 14, poll results. In the Literary Digest poll, Landon received 16,600, or actually that's 16,679,583 votes. So that is a count for the number of people that voted for Landon. So since this is a countable number, since it represents a count, then this is a discrete data set. It represents a count. There are gaps. There are gaps between the values that the data can take on. For instance, you can have one person that votes for Landon, but you can't have 1.5 or 1.37 or 1.28 people that vote for Landon. So therefore, there are gaps in the values that this data can take on. So therefore, this is discrete data. Now, number 16, Coke volume. The volume of cola in a can of regular Coke is 12.3 ounces. Now, 12.3 ounces is a bit tricky. 12.3 ounces, well, in that can of Coke, you could have 12.125 ounces, you could have 12.378 ounces, you could have 12.37958 ounces. So really, this volume in this Coke can could take on any value between 0 and some whatever the maximum value of this can could be, but it could be any number in that range, and there are no gaps or jumps or interruptions in the possible values that it could take on. So in this case, this comes from a data set that is continuous. So here we have the distinction between continuous and discrete data. And um, my statistics teacher actually told me that the difference is a quick way to think of it is to think about the difference between the number of eggs that a hen can lay, which would be discrete, it's 1, 2, 3, 4, 5, as opposed to the number of gallons of milk that a cow can produce, which would be continuous. Okay, now moving right along. We have our levels of measurement, okay? Now there are four levels of measurement here that we're going to talk about. The first one is the nominal level of measurement, and this is characterized by data that consist of names, labels, or categories. The data cannot be arranged in any order or scheme from highest to lowest, for instance. So that's nominal level data. There are no numbers really, they're just categories. The second level is ordinal level of measurement. And in the ordinal level of measurement, you can arrange it in some order, but the differences that you obtain from subtraction between data values either cannot be determined or have no meaning. So you can put it in some kind of order here, but the differences will have no meaning. Okay, the third level is the interval level, and it's just like the ordinal level, except with the additional property that the differences between any two data values are meaningful. However, the data will not have any natural zero or starting point. All right. Okay, now the last one is ratio level. And this is the strictest level. In ratio level is the interval level with the additional property that there is also a natural zero or starting point. And the zero indicates that there's none of that quantity present. So there's none of it there. So that's a natural zero. Okay, now let's take a look at some examples here. Okay, the first example, it says determine which of the four levels of measurement, nominal, ordinal, interval, or ratio, is most appropriate. 22, types of movies, either drama, comedy, adventure, or documentary. Well, that seems to me to be a nominal level because we're looking here not at numbers, but categories. So for number 22, since we're looking at labels or categories only, we would say that this is the nominal level of measurement. So this is nominal. Okay, now 24. Actual temperatures in degrees Fahrenheit. So actual temperatures in degrees Fahrenheit. Well, you see, temperature measures how much heat there is in an object. And in this case, we have at least an interval level. We have at least an interval level of measure because if we um, subtract 100 degrees from 50 degrees, we know that 50 degrees is 50 degrees less than 100 degrees. So the difference is meaningful somehow. Now, what we have to determine is if there is a natural zero for when we're measuring degrees Fahrenheit. Now, let's think about that. Is there a natural zero? Well, since temperature measures the amount of heat in an object, a natural zero for temperature would mean zero heat. And it turns out that in degrees Fahrenheit, 0 degrees Fahrenheit does not mean that there is zero heat present. That would mean there is zero motion. Doesn't mean that there's zero heat present in an object. So that zero is not a natural zero representing the absence of heat. So this is not a ratio level of measurement. This is actually an interval level of measurement. Actually, there is one temperature scale that is ratio level, and that's the Kelvin scale that they use in science. The Kelvin scale, with the Kelvin scale, zero is actually called absolute zero, and it actually represents the absence of heat or motion in the object. So the temperatures that we use, Fahrenheit and Celsius, are not ratio level because 0 doesn't represent the absence of heat, but there is a ratio level temperature measure called the Kelvin scale. Now 26. Measured amounts of greenhouse gases in tons emitted by cars listed in the data set 16. Okay, now this actually is a ratio level scale because not only are the differences meaningful, not only are there numbers here, but also a measurement of 0 would mean that there are 0 greenhouse gases in the air. So this is actually a ratio level because there's a meaningful 0. 0 actually means no greenhouse gases in the air. Number 28, ranks of cars evaluated by consumer union. Okay, the ranks of cars. Well, in this case, um, this is an ordinal level measure. And let me explain why. Well, in this case, um, they are being ranked, so they can be arranged in order, so it's not nominal. But in this case, the fifth ranked car is not necessarily 5 times worse than the first ranked car, so subtracting them doesn't necessarily give you anything meaningful. Um, and actually, this one is kind of a toss-up between ordinal and interval level. But I'm going to say that it is ordinal because I don't think that just because a car is ranked first, it's necessarily um, 3 times better than the car that's ranked fourth. So this would be an example of ordinal level measurement, and those are the levels of measurement.